So for this, let's write down a lemma that establishes this. So here's a claim. Okay, so if I have some g Zn to C and any t in Zn, okay, if I define g plus t such that g plus t of x is nothing but x plus t, then the claim is that g and g plus t have essentially the same Fourier coefficients. So what I mean here by essentially the same is that there is a little bit of difference, but this has a it's a multiplicative factor of 1. So it will not matter, like the magnitude will be the same. We will write it down. Okay, so what is the claim trying to do? It's trying to formalize this intuition that if I have two functions that are separated by some fixed t, then the Fourier coefficients don't change. Okay, so when I sample, I can hope to get something independent of t. So the goal, of course, here is I'm trying to gain independence from the colors, right? So that's what we are trying to do here. So let me prove this claim. Did everyone have a chance to write it down? Okay. Where? No. This is just any. This is not that S at all. So this is, give me any letter of your choice. U. I am just defining a membership testing function. So for any set, yeah, any arbitrary set. Thanks for pointing that out. This S is different from the period S. So this is just a set. Okay. And yeah, so what we are proving is that the Fourier coefficients of these two functions is going to separate only, going to differ only by a multiplicative factor of 1. So let's prove this. So the proof is not very hard, but I think it's worthwhile to do it so that we build our intuition well. So let's look at g plus t gamma, the Fourier coefficient. So g plus t hat gamma. So this by definition is expectation over g plus t x and chi gamma x star, right. So this is just by definition. So this is just rewriting, yeah, and now I am just going to change variables. Okay, so I'll let x plus t be y. Okay, so now this will become expectation over y, g of y, chi gamma y minus t, not x, y minus t conjugate, right. And because we know that chi is a character, so I will get I can split the y and the t. Okay, and also the conjugate and the minus t will, the minus of the minus t will cancel. So I will end up with this. Okay. So now here this this chi gamma of t can be brought outside, right. So this chi gamma t can be brought outside and I get E y g y chi gamma y conjugate. So, this is nothing but maybe I will even open it up right away. So, this is nothing but omega to the gamma t g hat gamma. Okay. So, what did we show? We showed that g hat, so the Fourier coefficient of g plus t gamma, so g plus t hat gamma is equal to g hat gamma times omega to the gamma t. Okay. Now, since omega is a nth root of unity, right, this is a complex number of magnitude 1. Does everybody agree? Okay. So, this is what we were claiming earlier. Okay. So, now we will use this. So, basically what we get, this implies that the g plus t hat gamma squared is nothing but omega to the gamma t g hat gamma the whole squared, right, which is g hat gamma the whole squared. Okay. So, what is this saying? Now, this is saying, so this is the probability with which I measure a given gamma, right. In the Fourier, like after applying QFT, whatever state I get, right, it is some summation of g hat gamma gamma, right. And so, when I measure that, I get some gamma with probability g hat gamma the whole squared. So, this is saying that this probability is really independent of t. That is what this is saying, right. So, t for us is obviously the color, I mean the offset between the colors, right. So, if I have whatever red, green, whatever colors I have, right. So, the t is sort of the distance between any two colors in this set. So, this is saying that essentially once I apply the QFT, what I get is really something independent of the color. I get some state, right, it is some summation over gamma with some coefficients, right, and when I am going to measure, I am going to get some state with some probability. This probability is really independent of the color. Does everyone agree with that? Yeah. So, that is what is really the main thing that is going to help us here, right, because basically now what this says is that if so we are not done yet, right. So, we have to show that what remains actually. Can you tell me what remains to get to where we want to go? What is the big step that remains? I have to show that when I apply this QFT, I get some state which is some sort of meaningful superposition. So, in particular I should be able to argue that these are all states that give me some meaningful information about S, right. So, previously we had that okay, these are states that are separated by S, right, inputs are separated by S. Now, having applied the QFT, what did it become? So, I need to still argue that somehow when I measure, I get some gamma which is something related to S, right. It gives me some information about S, and that by repeating this many times I can hope to recover S, right. So, previously we had these these incompatible offsets when we were measuring, and now we have shown that okay, at least this dependence on color is gone, but it remains to show that whatever are the states with non-zero probability on them, these should be somehow related to S, right, and in fact they will be multiples of n over S. Okay, this is also intuitive when we take QFT, but we will prove that. Okay, so instead of being offset by multiples of S, now we will show that they are offset by multiples of n over S, and moreover because the color does not matter, we can just think of the color 0. So, we can just fix our attention to sort of 0, n over s, 2n over s and so on and so forth. And now when we measure, we will get some k n over s and k prime n over s, and we will hope that the GCD gives us n over s and therefore s. Okay, this is where we will go with this. So, let us write this proposition. So, let the set H be all multiples of our period S in Zn. Okay, and also I am defining this new function small h as the indicator function for big H. Okay, so h of x is basically 1 if x is in this set H. Okay, and now I am claiming that h hat of gamma is 1 over s if gamma lives in this set. Okay, and is 0 otherwise. So, I still need to prove this claim, but at least I hope that everyone agrees that this is kind of exactly what we want, right. What is this saying? That if I fix my attention to these, sorry, I wrote this wrong, I forgot the n over, wait. So, I think I said it correctly, it is n over s, fine, I will just write this again, it is n over s, 2n over s and so on. I hope I did not, yeah, here there is nothing. Yeah, because remember we were talking of multiples of n over s, right. So, now what are we saying? We are saying that if I look at all these multiples of n over s, okay, then what we are saying is that this this function h, this has it has its Fourier coefficient is 1 over s when gamma belongs to h and it is 0 otherwise. Now, you may wonder why am I looking at this h instead of my original function. We will just connect them. So, let me, instead of proving the proposition first, let us first see how to use the proposition and then we will go back and prove it. Okay. So, good. So, let us look at our, let us go back and consider the state we had. So, consider the state. So, do you remember what it was? So, let us go back and recall what our state was, right. So, this is our input state. So, it is the summation of FCXX, right, and now we will be applying our QFT to this state, right. So, let us write down our state. So, our state, maybe I will just write the whole thing once. So, we had square root s FC x, right. And now, because I proved independence of color, okay, I can simply get rid of this C in the F. So, I am going to rewrite this as summation over x square root s h of x and x. Okay, so actually I have made a typo, wait, I am sorry. So, this I wrote correctly, this is incorrect, let me just correct myself. Okay, so what is our proposition? If I let h be 0 s, 2 s and so on. Okay. And let small h be the indicator function with respect to h. So, it's the h that we had written first. So, we corrected the wrong thing. So, I had written gamma in h, but in fact gamma needs to be in 0 n over s, 2 n over s and so on. Okay. Is it clear for everyone? So, this is our proposition. Okay. So, let h be 0 s, 2 s and all multiples of h. Let small h be the indicator function for this. Okay. And now our proposition is saying that h hat of gamma is 1 over s if gamma is in the multiples of n over s and it is 0 otherwise. Okay. So, now let us consider the state that we are at. Okay. So, what we have done is we have used our independence of color to rewrite to rewrite our function in this way. Are there any questions about this? Okay. So, now when I apply my Fourier transform, what we get is summation over gamma root s h hat of gamma gamma. And then if we measure, we get gamma with some probability s times h hat gamma squared. Sorry. So, now if our proposition is true, okay, then what this means is that the only points that have so let us go back to our proposition. So, the only points that have a non-zero probability are the points that are multiples of n over s, right. So, we are going to we will analyze what probability we get it with, but whatever it is, we are going to get some point from that set. Okay. So, this is basically the final algorithm. I mean, I am going to keep sampling, I will get multiples of n over s, okay, and then I will take the GCD. I have to bound the probability that things do not go wrong, we can do that, but finally this is all that we want. Okay. So, this will help us recover s and that is what we wanted. Okay. So, now we will figure out what is this probability and we will prove the proposition. Okay. So, yeah, so what is the probability with this probability and what is this probability? It's 1 over s in fact. Okay. So, let us write that. So, since by our proposition h hat of gamma is 1 over s if and only if gamma is in H, we get gamma in H with probability s times 1 over s the whole square, which is 1 over s. Okay. It is fine? Yeah. So, h hat of 1 is 1 over s by our proposition and we have s times h hat the whole squared. So, that is s times 1 over s squared. So, that is 1 over s. Okay. So, that is good. So, we are going to sample, so in the set we will sample a uniform element. Okay. Okay, so now it remains to prove the proposition, right. So, proof of the proposition. So, we want to compute h hat of gamma. Okay, this is by definition expectation over x of hx chi gamma x conjugate. Okay. Now, note that you know h by its definition uh, only takes non-zero values in the set H, right. So, small h by definition, it only takes a non-zero value when x belongs to this particular set S, right, or H, capital H, this one. Okay. So, therefore, I can write this expectation as 1 over S chi gamma x the whole star. Okay. And let us compute this. So, when gamma is in the set 0, n over S, 2 n over S and so on, okay, then chi gamma of x conjugate, right, which is omega to the minus gamma x. I would like you to tell me what this is going to be. So, the question is that when I have gamma in this set, what is chi gamma of x conjugate? Why is it 1? So, basically our x here is a multiple of S and our gamma is a multiple of n over S. So, that is why the S cancels and you get a multiple of n, right, and omega to the n is 1. So, that is why you are going to get you know omega to the some multiple of n. Let me write this down. Okay, I will even recap it a little bit for the new page. So, since x was sampled so I hope that this is not confusing, right. So, this is basically because where is our h hat gamma? Yeah. So, here, right, when we first take the expectation, this is x in Zn, but we observed that Hx is non-zero only when x is in H, right. So, here we have restricted our expectation to this set, right. So, that is why H is always a multiple of S, right. And now we are just considering just you know we are just looking at what happens if gamma belongs to this set. So, of course, you have to worry about what happens when gamma does not, but we will analyze this case first. So, in this case this ends up being 1 since x was sampled from H and gamma is in 0 n over S etc, right. X times gamma is a multiple of n. So, chi gamma x conjugate, right, this is 1. Okay. So, now h hat of gamma which we were trying to figure out, okay, we said that this is 1 over S the expected value of x, x in H chi gamma x star, right. So, this is 1 over S. Does everyone agree with this computation? Any questions? Okay, so h hat of gamma is 1 over S. So, now why were we computing h hat of gamma? Well, we want to figure out the probability of sampling a particular state, right. So, now let's look at what happens when your gamma is not belonging to this set. Okay. So, here I want to claim that the probability of sampling a gamma which does not belong to this set of multiples of n over S, I want to claim that this probability is 0. Can you tell me why? Exactly. So, there are S many n over S's, right. So, our set H that that we defined, the set which has 0 n over S and so on, has cardinality S. Okay. So, this set has cardinality S. This is a simple exercise. Okay. So, you have sort of these integer multiples of n over S, right, and yeah, so you can check this for yourself. So, there will be S of these. Okay. It needs a little bit of care, but it is easy enough to see. So, now if my set has this cardinality, right, now let me look at the probability of getting a gamma in this set. So, what is the sum of probabilities when I look at gammas in this set, right? What is the probability that I get a particular gamma? So, h hat of gamma is 1 over S, right. So, that means that what is the probability of getting gamma? So, let us look at the state that we had. So, this was our state, right. So, the probability is actually square of root S h hat gamma. So, that is S times h hat gamma the whole squared, right, which is S times 1 over S squared, which is S. And now, if I add up all the probabilities over this set, I get 1. So, this means that I have used up all the probability in this set itself. So, there is no probability to give to any other set. So, this means that I will always get something from this set. Okay. So, let me just finish writing this. So, this set has cardinality S. Now, the probability of sampling some gamma in this set this is square root S h hat gamma the whole squared, right, which is S times 1 over S the whole squared, right, which is 1 over S. And now, because there are S of them, the total probability of sampling in this set is therefore 1. So, what this shows is that at this stage when I sample, right, I will always get a gamma from this set of multiples of n over S. Is it clear? So, we are looking at this set and we have shown that all the probability is on this set itself. So, that is it. So, basically we are done at this stage.